Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 15, and it is entitled Newton's Second Law and Elevator Problems. In this lesson, we begin grappling with one of the central concepts in this course, figuring out how unbalanced forces influence the motion of objects. Forces do this by accelerating the object, thereby changing the object's velocity. This topic is often referred to as dynamics, and it will arise over and over and over again all year long. A good place to begin is to recall Newton's first law, the law of inertia. Remember that the first law says that an object will move at a constant velocity, which means it will move at a constant speed and in a straight line unless acted upon by an unbalanced force. The object might not be moving at all, in which case its velocity is zero. We've used Newton's first law to solve what we call equilibrium problems, in which several forces act on an object. The object isn't accelerating, and we've been able to balance the forces and discover what the unknown force was as a result of this balance. We sometimes had to break forces into horizontal and vertical components, and we succeeded in puzzling out the missing pieces. Now, suppose that there is an unbalanced force. Newton's second law, which is a workhorse of an equation that gives us a way of predicting the motion of the object and how the object behaves under the influence of this unbalanced force, is the way that we'll proceed. Newton's second law is an application of common sense. It tells us that the harder I push on an object, the more the object will accelerate. It also says that the more inertia the object has, which we'll measure numerically through the mass, then the less the object will accelerate, meaning that the more the object will resist changes in its velocity. So, what is Newton's second law? Here's the equation, and it looks like this. The acceleration is equal to the net force divided by the mass. This equation has acceleration on the left side. It's a vector quantity, meaning it has both a numerical value for its magnitude and a direction in which it's pointed. Remember also that acceleration equals the change in velocity with respect to time. So, when an unbalanced force acts, then the object's velocity will change. On the right side of Newton's second law, the numerator consists of a sigma f. That's a capital Greek letter sigma, meaning the sum of all the forces. And so I'll have to combine all the forces acting on the object in a vector way to figure out the net effect of a combination of forces. It may be that there's only one force acting, or it may be that there are several. But whatever forces are at work, I'll add them together and get what we call the net force, sigma F. Down in the denominator of Newton's second law is the mass, the numerical measure of the object's inertia. This equation says three things. First, it says that the acceleration is in the same direction as the net force. In other words, the velocity changes occur in the same direction as the direction of the net force. Second, it says that the acceleration is directly proportional to the net force. I'm using a tilde sign to represent is proportional to. The more the net force is, the more the acceleration occurs. As the net force increases, so does the acceleration. Both the net force and the acceleration appear in the numerators on each side, so that's a direct proportionality. Third, Newton's second law says that the acceleration varies inversely with the mass. And this makes common sense. The more inertia the object has, the more it resists changes to its motion. If I exert a force on a little red wagon to make it move, and I try to exert the same force on my big Dodge pickup truck, the truck will resist changes to its motion more than the little red wagon does for the same given force, because the truck has more inertia. It has more mass. It's harder to change its motion. Now let's pause just briefly to acknowledge the vector nature of these motion quantities. Acceleration is a vector, velocity is a vector, and displacement is a vector. These are all related to each other, but they aren't the same thing as each other. And frequently, when we talk about an object's motion, folks will confuse two or more of these quantities. Most often, students confuse velocity and acceleration. Again, these concepts are related, but they mean different things. The point is that we may not be able to just look at a moving object and tell whether it's accelerating. Just because it's in motion doesn't mean that there's an unbalanced force acting on it. Oftentimes, folks think that because an object is moving, then the object must be accelerating. And this ain't necessarily so. It could be that the object is moving with a steady speed and in a straight line. It doesn't mean that there are no forces acting on it. The forces could be balanced by something else. So, for example, a car that's moving along at interstate speeds along a straight stretch of road is moving at a constant velocity. And certainly the wheels are pushing the car along the road. But that pushing force doesn't constitute an unbalanced force. The wind is pushing the car just as hard in the opposite direction, and the car moves at a steady speed. The point is this: don't confuse acceleration and velocity and displacement. With that caveat said, let's move on. We usually think of accelerating as picking up speed, but in fact, acceleration can cause an object to lose speed too. Picking up speed means going faster and faster, while losing speed means getting slower and slower. Technically, both of these are accelerations. Likewise, an acceleration can cause an object to change its direction. You remember that velocity is a vector quantity, so anytime the direction of the velocity changes, then we say the object is accelerating. We have names for these types of acceleration. When an object changes its speed, we say that the object experiences linear acceleration. When an object changes its direction, we say that the object experiences centripetal acceleration. It's possible that an unbalanced force changes the object's direction without changing its speed. Such an object, like a child riding on a carousel or a coin sitting on a spinning turntable. If the platform is moving at a constant rate, then the child or the coin has a steady speed, but the direction of the velocity is constantly changing, and the object undergoes what we call uniform circular motion. It experiences only centripetal acceleration. Generally speaking, objects will be changing both their speed and their direction, and those problems can be tough to solve. We'll start by considering linear accelerations, and later we'll pick up centripetal accelerations. We leave the combination of linear and centripetal acceleration to more advanced courses than this one. Now what we want to do is to use this very powerful but deceptively simple appearing equation, Newton's second law, to solve numerical problems. We'll begin with problems in one dimension, and we'll start with a class of problems sometimes called elevator problems. First off, you should know that elevator problems aren't just confined to elevators. They involve any kind of object that's moving upward or downward that has forces in addition to the gravitational weight force. It could be a rocket. It might involve a scale. It might be an object pulled upward by a cable or a string, like a crane lifting some construction materials. You could be talking about helicopters. Whenever there is strictly vertical motion where gravity isn't the only force involved, these problems are all lumped together under the heading of elevator problems. Typically, these problems are stated in such a way that the object is moving vertically, then something happens and you have to predict various things involving the object's motion. Let's sketch a diagram of a person that's standing on a scale resting on the floor of an elevator, and then let's address some of these sometimes confusing vocabulary words invoked in these problems. Here's a scale sitting on the floor of an elevator, and here's a rider standing on the scale. As this person rides the elevator and reads the scale, what's going on? Well, let's sketch a free body diagram showing the forces acting on this person. This dot represents the person's center of mass. The earth pulls this person downward. The scale pushes this person upward. As this person rides, she experiences two forces. The earth pulling her downward is called her weight, or the gravitational force. Also, the scale pushes her upward. And since the scale's horizontal platform exerts a vertical force on her, then this is a type of normal force, normal meaning perpendicular. The horizontal platform pushes vertically upward. What makes these problems challenging can be the unclear language that's used to talk about what the rider experiences and the numerical readings she's taking while she's riding. Sometimes the terms actual weight and apparent weight appear in these problem statements. When we look at the free body diagram and we see that only these two forces act, then one of these forces varies while the other one remains constant. The earth pulling the person downward doesn't change as the rider moves along inside the elevator. This force is steady throughout the ride, no matter what happens along the way. On the other hand, the reading on the scale, the apparent weight, will vary according to what the elevator is doing. Often the problem will state something to the effect of, what will be the apparent weight when such and such happens? What you're looking for in this case is what is the reading on the scale. The reading on the scale is the normal force that's acting on the person. If there's no acceleration, then the reading on the scale will equal the actual weight, whether the person is moving or not. But the reading on the scale will vary when acceleration is occurring. If the acceleration is upward, then the scale reading is bigger than the actual weight and the person feels heavier. They actually experience a difference feeling in their legs than they do when they're moving at a constant speed. On the other hand, if the acceleration is downward, then the apparent weight is a number that's less than the actual weight, and the person feels lighter. Their knees actually help to lift them up as the elevator experiences a downward acceleration. But in whatever way these problems are stated, the approach to them is to sketch a free body diagram and then write Newton's second law, employing the forces shown in the free body diagram. Now let's apply this approach